We are living through one of the most extraordinary periods in human history, a time of discovery unlike any that has come before. Humanity is learning more about the universe than ever before, and we are doing so at a pace that would have seemed impossible just a few generations ago. Of all the remarkable discoveries being made in this golden age of astronomy, perhaps none captures our imagination quite like the revelation that there are other planets, other worlds orbiting distant stars far beyond our solar system. These are the exoplanets, and their discovery has fundamentally changed how we understand our place in the cosmos. Today, the existence of exoplanets is something we take for granted. We hear about new discoveries regularly, and the idea that planets orbit other stars seems almost obvious. Yet it is worth pausing to appreciate just how recent this knowledge is. Only a few decades ago, at the end of the 20th century, we had not seen a single exoplanet. Not one. The discovery of the first exoplanet around a sun-like star happened in 1995, and when it was announced, much of the scientific community was skeptical. The planet that was discovered was too large, too close to its star, too different from anything in our own solar system. Many astronomers simply did not believe the findings at first. Before this breakthrough, the search for planets beyond our solar system was considered by many to be a waste of time and resources. Nobody thought this was even worth studying. The conventional wisdom held that detecting such planets was impossible, given the limitations of our technology and the vast distances involved. It was definitely a taboo subject in mainstream astronomy. Researchers who wanted to pursue this line of investigation risked damaging their careers by focusing on something that most of their colleagues viewed as a fool's errand. But those few brave pioneers who dared to search for exoplanets despite the skepticism found something that never ceases to amaze us. What they discovered has opened up entirely new fields of study and transformed our understanding of planetary systems. Nature, it turns out, did not obey the laws and assumptions that we had confidently set for ourselves based solely on our experience with our own solar system. And that was exciting in ways that are difficult to overstate. Everything we are finding outside our solar system is exotic, strange, and wonderful. The types of exoplanets that exist in the galaxy are limited only by our imagination, and sometimes they exceed even that. These are real places that we can point to in the night sky and describe in astonishing detail. There are planets where it rains diamonds from clouds made of vaporized rock. There are worlds where sulfuric acid falls from the sky. There are planets with surface temperatures hot enough to melt iron, and others that are frozen solid. There are worlds with multiple suns in their skies, and planets where one hemisphere is locked in eternal day while the other endures perpetual night. But this incredible quest to find and understand exoplanets has a deeply human face as well. It is driven by one of the most profound questions we can ask. At its core, the search for exoplanets is really about searching for ourselves, or at least for others like us. In the heart of every astronomer working in this field, there is a desire to go out there and find a planet with oceans and continents and breathable air. A planet that is just like Earth. A world where life as we know it could not only survive, but thrive. Humans have always been fascinated by the heavens above us. We have wondered about the stars for as long as we have existed as a species. And we have always asked ourselves what our place is within the vast cosmos. Since ancient times, people have looked up at the night sky and seen the stars rotating overhead in their regular, predictable patterns. Because the celestial sphere appears to rotate around us each night, it was natural for our ancestors to assume that we were at the center of this never-ending spectacle. The Earth seemed stationary beneath our feet, while everything in the sky revolved around us. For thousands of years, we used to think the Earth was the center of the universe, that the planets and stars all revolved around our world. This geocentric model of the cosmos made intuitive sense based on what people could directly observe. It also placed humanity in a privileged position at the center of creation, which appealed to religious and philosophical sensibilities. Then, in the 16th century, a Polish polymath and Catholic canon named Nicolaus Copernicus upset this comfortable status quo through careful mathematical analysis and astronomical observation. Copernicus figured out that the apparent motion of the stars in the night sky was more likely due to the Earth moving through space rather than the stars themselves moving around us. He proposed that the stars were actually fixed in place in the distant heavens, and what we perceived as their motion was actually a result of Earth's own rotation on its axis and its orbit around the sun. Copernicus came along with a revolutionary new theory that fundamentally challenged the prevailing worldview. He proposed that the planets, including Earth, actually revolved around the Sun rather than everything revolving around Earth. This heliocentric model of the solar system was considered heretical by many at the time. It contradicted not only the established scientific consensus, but also certain interpretations of religious scripture. The idea that Earth was just another planet, not the center of creation, was deeply unsettling to many people. Suddenly, with this shift in understanding, humankind was no longer at center stage in the cosmic drama. We had been demoted from our privileged position. But there was worse news to come as our understanding of the universe continued to expand. Over the following centuries, as telescopes became more powerful and astronomers made more detailed observations, it turned out that not even the Sun occupied the center of everything. The Sun, we eventually learned, is just one star out of a few 100 billion stars that make up the Milky Way galaxy. All of these stars, including our Sun, orbit around the center of the galaxy in a vast cosmic dance that takes hundreds of millions of years to complete. And the Milky Way itself is just one galaxy out of probably a few 100 billion galaxies that exist throughout the observable universe. Each of those galaxies contains hundreds of billions of stars of its own. The scale of the cosmos is almost incomprehensibly vast. Over the centuries, as telescopes became increasingly powerful and sophisticated, they revealed a universe that was both teeming with countless stars and yet so unimaginably vast that it is mostly empty space. The distances between stars are enormous beyond our ability to easily visualize them. To get a sense of the scale we are dealing with, consider this thought experiment. If you were to shrink our Sun down to the size of a single grain of salt, then the Earth would be located about 2 inches away from that salt grain, and Earth itself would be almost microscopic at this scale, roughly the size of a particle of smoke floating in the air. That gives you some sense of the size difference between Earth and the Sun. But here is where it gets really mind-boggling. If you wanted to place another grain of salt to represent the next closest star to our Sun, where would you put it? That next salt grain representing the nearest star would need to be placed 7.5 miles away from the first one. 7.5 miles of mostly empty space, with just the tiny grains of salt representing the stars, and dust particles too small to see representing the planet's dots. So we are, in a very real sense, just a dust grain floating out there in the immense emptiness of space. Our entire world, everything we have ever known, every person who has ever lived, all of human history, has played out on this cosmic speck of dust. But even so, it might be that we are the only very interesting dust grain out there in all that vastness. Perhaps we are unique in the universe, the only place where life has arisen and evolved into conscious beings, capable of contemplating the cosmos. But many scientists, including those working on exoplanet research, do not think that we are alone. The thing that really drives all of this work is a fundamental question. Is there life elsewhere in the universe? This question has fascinated philosophers and scientists for centuries. But only now are we beginning to develop the tools and techniques that might allow us to actually answer it. This is perhaps the most fundamental question that we can ask in astronomy. Are we alone in the universe, or is life common, perhaps even abundant, scattered among the stars? The sheer number of stars in our galaxy and beyond certainly suggests that worlds like our own must exist elsewhere in the cosmos, with hundreds of billions of stars in our galaxy alone, and hundreds of billions of galaxies in the observable universe. The odds seem to favor the existence of other Earth-like planets, and where there are Earth-like planets, there might be life. But at the end of the 20th century, despite all of our philosophical reasoning and statistical arguments, there was no actual empirical evidence that exoplanets existed at all. We had never seen one, we had never detected one by any method, and most astronomers believed that theorizing about exoplanets and their potential to host life was a pointless exercise. The planets around other stars were simply too small and too far away to be observed with any technology we possessed, or could reasonably expect to develop in the near future. Asterisk, in the early 1980s, those astronomers working in the field knew in their hearts, from a philosophical perspective, that exoplanets must exist. It seemed illogical that our solar system would be the only one in the entire universe. But in astronomy, as in all sciences, evidence is king. Philosophical arguments and statistical reasoning count for nothing without observational data, and until you actually see an exoplanet and can confirm its existence through repeated observations, There's always a nagging doubt. Could we really be alone after all? Asterisk, the question of exoplanets seemed like an itch that could never be scratched, a mystery that would forever remain beyond our ability to solve. But then, in 1983, a new kind of telescope was about to challenge those pessimistic assumptions and open up an entirely new way of seeing the universe. Asterisk, the infrared astronomical satellite, known by its acronym IRAs, was launched into Earth orbit. This revolutionary telescope exploited new technology that was sensitive to infrared light, which exists beyond the range of human vision. Infrared astronomy involves detecting wavelengths where you are essentially seeing heat rather than what ordinary people would call visible light. Asterisk, all objects in the universe that have any temperature above absolute zero emit some level of infrared radiation. Although this radiation is invisible to our eyes, we can sometimes feel it as heat on our skin. We are used to the idea that with an infrared camera, we can see people or animals at night even when it is pitch black to our normal vision, because warm living things show up clearly by their infrared radiation against the cooler background. Asterisk, IRAs applied this same principle to astronomy, conducting a survey of the entire sky in infrared wavelengths. The key advantage of infrared observation is that it gets to places that visible light cannot reach. Infrared radiation can penetrate clouds of dust that completely block visible light, allowing us to see through these cosmic veils. Asterisk, the space between stars is filled with vast bands of gas and dust that absorb and scatter visible light, completely blocking our view of whatever lies behind them. But the longer wavelengths of infrared radiation pass through these cosmic clouds much more freely. So stars that were previously hidden from us, surrounded by cocoons of dust that absorb their visible light, were suddenly revealed by IRAs, detecting their infrared emissions. Asterisk, at the time, there were astronomers working on infrared technology for large telescopes here on Earth. So the astronomical community knew a lot about what IRAS was doing. In some ways, the technology was really quite crude by today's standards. The telescope would simply point at the sky and let the rotation of the satellite slowly scan across different regions. When a bright infrared source came into the field of view, the detector would register it, and gradually, bit by bit, IRAs would map the entire sky in infrared light. Asterisk, the survey discovered thousands, even millions of new objects that had been invisible to previous telescopes operating in visible wavelengths. It was a revolution in astronomy, opening up an entirely new view of the universe. Asterisk, around 6 months into the survey, IRAS detected something truly bizarre in the infrared signature coming from a star called Beta Pictoris, which is located 63 light-years from Earth. Beta Pictoris had all this extra infrared radiation that was completely unexpected. It was not part of the normal thermal spectrum that you would expect from a star of its type and size. The infrared emission was clearly not coming from the star itself. Asterisk, so if the infrared radiation was not coming from the star, where was it coming from? It was a real puzzle that nobody could immediately explain. Scientists had no idea what could be causing this anomaly, and that began a major detective story in the astronomical community. Asterisk, news of the Beta Pictoris anomaly eventually reached a remote observatory in Chile, where the NASA astronomers named Richard Terrill and Bradford Smith decided to pause their ongoing survey of objects within our own solar system to investigate this mysterious star. They thought that perhaps there was some material in the vicinity of Beta Pictoris that was being illuminated and heated by the star, and this heated material was generating the excess infrared signature that IRAs had detected. Asterisk, it was a tantalizing piece of evidence that maybe there was something interesting out there that astronomers should be looking for more carefully. The location of this telescope in Chile was quite remarkable. It sat on the end of a ridge, almost like the prow of a ship, where the landscape fell away dramatically on 3 sides. It was a rather beautiful and isolated location, but more importantly, for astronomy, it enjoyed very, very dark and very, very clear skies, making it an ideal place for observing faint objects. Asterisk, in the spring of 1984, the astronomers turned their optical telescope toward the area of the Milky Way where Beta Pictoris was located. At first, Beta Pictoris appeared to be a star like any other star in the sky, one of thousands upon thousands of similar stars visible in that region of space. But when Richard and his colleague tried to observe what could be causing the infrared excess around the star, they ran into an immediate problem. Asterisk, at the telescope Looking directly at Beta Pictus, you really could not see anything unusual at all. This was because the central star itself was hundreds of millions of times brighter than any material that might be surrounding it. Any faint structures around the star were completely overwhelmed by the brilliant glare of the star itself. Richard's only option was to try to artificially blot out the light of the star by creating a tiny sunshield. Astronomers call this device a coronagraph, named after similar instruments used to study the sun's corona during solar eclipses. A coronagraph is basically a way of putting your thumb over the bright star, so to speak, allowing you to look at much fainter material in the immediate vicinity around the star that would otherwise be invisible. Coronagraphs are usually precision-engineered instruments requiring careful manufacturing and calibration, but Richard would need to improvise his artificial eclipse, using whatever supplies were available at the remote observatory. He ended up using rub-on transfer letters from the stationery cupboard, the kind that were commonly used before desktop. Publishing became widespread. These transfer sheets included periods or dots of various sizes. Richard selected a period that was about 0.5 millimeter in diameter. He needed to suspend this tiny dot at exactly the right position in the optical path of the telescope. He created a mounting by making a cross from two thin wires, and at the very center of this cross, he carefully fixed the tiny period from the transfer sheet. This would serve as his improvised occulting mask. When they looked at Beta Pictus with this jury-rigged coronagraph in place, the results were stunning. Suddenly, an extended disk of material surrounding the star showed up clearly in their images. They could see a flattened disc-like structure extending out from the star, like the rings of Saturn, but on a vastly larger scale. What appeared in their images looked like the bright spikes, or extensions sticking out on either side of the star. They were seeing dust particles, not emitting in the infrared as IRAs had detected, but actually reflecting the visible light from the star at the center. This structure was soon identified as what astronomers call a debris disk. A debris disk is really the fallout of the planet formation process. It consists of dust particles created from collisions between larger objects like asteroids, comets, and rocky planetary bodies. The existence of this debris disk around Beta Pictus was strong evidence that there was, or had been, a process of planet formation occurring around this star. In other words, they were seeing the first evidence of a planetary system beyond our own solar system, even if they could not yet directly observe any actual planets within it. It was incredibly exciting for everyone involved. This was the first real evidence of what could be described as the birthplace of planets around other stars. The debris disk provided a tantalizing hint that planet formation might be a common process in the universe, not something unique to our own solar system. Richard Terrell's groundbreaking image of the Beta Pictus debris disk created quite a buzz of anticipation in the astronomy community, particularly among those who harbored hopes of eventually detecting actual exoplanets. Could exoplanets actually be within our grasp after all? The disk around Beta Pictus really opened people's eyes to new possibilities. Maybe the field of exoplanet research was finally ready for prime time. Maybe this was not such an impossible dream after all. But detecting an actual exoplanet was a very different challenge from photographing a debris disk that spanned a region larger than our entire solar system. A debris disk reflects a lot of light and extends over a large area, making it relatively easy to observe once you block out the star. An actual planet, on the other hand, is tiny by comparison and reflects far less light. A decade after the discovery of the Beta Pictus debris disk, exoplanets themselves were still strictly the subject of theoretical speculation. In the early 1990s, astronomy had no confirmed exoplanets whatsoever. Nobody had found anything that could be definitively identified as a planet orbiting another star. The field of exoplanet research as a serious scientific discipline did not really exist at all. When a young astronomer named Didier Queloz began his doctoral studies in astrophysics at the age of 26, he wisely chose to focus on more mainstream, established areas of research rather than risk his career on the dubious prospect of finding exoplanets. His doctoral supervisor was Michel Mayor, who had built a solid reputation studying binary stars. That was the business they were in, and it was respectable, well-established astronomy that would not raise any eyebrows among their colleagues. Astronomers had been studying binary stars, systems where the stars orbit around each other, for many decades. Binary star systems are locked in complex gravitational interactions that produce observable effects. The task that Queloz was given for his doctoral research was to help unravel the intricacies of these gravitational dances. The core of his doctoral work involved designing a new piece of equipment called a spectrograph. This instrument needed to be precise enough to detect tiny changes in the velocity of a star as it moved through space. These subtle speed changes of a large star can reveal the presence of a much smaller companion star orbiting around it, because the gravitational pull of the companion star as it orbits causes the primary star to appear to wobble slightly. The phenomenon works like this: when the objects orbit each other, they actually both orbit around their common center of mass. For a binary star system with two stars of similar size, the center of mass is somewhere between them, and both stars trace visible orbits through space. But even when one star is much larger than the other, the smaller companion still exerts a gravitational pull that causes the larger star to wobble slightly in its motion through space. By carefully measuring how much the star wobbles, astronomers can determine the mass and orbital characteristics of the companion star. The size of the wobble directly reflects the mass of the unseen companion, and if there is no companion star at all, then there will be no detectable wobble in the star's position or velocity. To be able to detect even the smallest companion stars, Queloz knew he would need to measure velocity changes of approximately 50 meters per second, which is about 110 miles per hour. This was no easy feat in a universe of constant and often violent motion. Everything moves fast in space, and distinguishing a tiny wobble from the general background motion is extremely challenging. The motion of Earth itself on its orbit around the Sun proceeds at about 100,000 kilometers per hour, so astronomers have to account for and subtract out all these massive changes of velocity in order to isolate the tiny signal they are looking for. As Queloz described it, trying to detect these small velocity changes is like trying to measure the speed of a snail crawling on the wing of a jet aircraft as it flies through the air. The snail probably would not survive on the wing in reality, but that gives you a sense of the scale of the challenge. Queloz's spectrograph exploited the latest advances in computers and fiber optics available in the early 1990s. The performance of the instrument turned out to be a pleasant surprise even to Queloz himself. He had set a goal to reach a precision of 50 meters per second in measuring stellar velocities, but the instrument completely overshot that goal. The actual performance was much better than expected. They ended up with an instrument that could reliably measure velocity changes as small as 15 meters per second. To put that in perspective, they were now talking about detecting velocity changes equivalent to the speed of a person running, not a racing car or jet aircraft, but a human runner. This was an incredible achievement in precision measurement. Queloz quickly realized that this unexpected extra sensitivity to velocity changes meant that his spectrograph could potentially detect objects much smaller than companion stars. With this kind of measurement accuracy, you opened up a completely new window of investigation, which was the detection of planets rather than just stars. An exoplanet orbiting a star would cause an even tinier wobble than a small companion star. But now that wobble might just be detectable with this new instrument. But like all aspiring astronomers trying to build a career, Queloz was well aware that exoplanet hunting was seen as a highly disreputable occupation at best, even bordering on pseudoscience in the eyes of many established astronomers. Back in the early 1990s, it was still considered ridiculous to search for exoplanets. To seriously propose studying them would have been laughable to most of the astronomy establishment, and it was definitely still a taboo subject that could harm your professional reputation. Making the wrong decision about research focus could spell career suicide. For a young astrophysicist who did not yet have tenure or an established reputation, Queloz remembered clearly that Michelle Mayer told him very directly, "Look, Didier, you need to understand that you are not going to find any planet using this instrument. Is that okay with you?" And Queloz agreed, saying yes. Of course, he understood the risks and the low probability of success, because it was nevertheless extremely cool and worthwhile for him to demonstrate that the machine had the technical capability to detect a planet, even if no planets were actually found. In September of 1994, Didier Queloz began his search for exoplanets from a telescope facility located high in the mountains of Provence in southern France. Meanwhile, his doctoral supervisor Michelle Mayer went on vacation to Hawaii, confident that he would not be disturbed by any dramatic discoveries while he was away. Queloz had compiled a list of 142 stars that had been chosen because of their similarity to our own sun. The reasoning was that if planets were going to be found anywhere, they would most likely be around stars similar to our sun. One of these target stars was designated 51 Pegasi. 51 Pegasi is a star located in the constellation of Pegasus. Sitting approximately 48 light-years from Earth, Queloz was looking for telltale signs that this star was wobbling slightly due to the tiny gravitational pull of an unseen exoplanet as it orbited the star. The technique worked like this. You take the light from the star and you spread it out into its component wavelengths using a prism or diffraction grating. You create what is essentially a rainbow, which astronomers call a spectrum. Within this spectrum are dark lines at specific wavelengths, created by elements in the star's atmosphere absorbing light at those particular wavelengths. Now, when the star moves toward or away from us, these absorption lines shift slightly in wavelength due to the Doppler effect. Motion toward us shifts the lines toward bluer wavelengths, while motion away from us shifts them toward redder wavelengths. These are very tiny shifts in wavelength, and measuring them requires great precision, but by carefully tracking these shifts, you can build up measurements of what astronomers call the radial velocity of a star, meaning how fast it is moving either toward us or away from us along a line of sight. If a planet is orbiting the star, this will cause periodic changes in the star's radial velocity as the star wobbles in response to the planet's gravitational pull. The gravitational tug of an exoplanet would cause periodic changes in the star's velocity, comparable in magnitude to the running speed of an Olympic sprinter. This is what Queloz was hoping to detect, but immediately, the very first data from 51 Pegasi made Queloz question whether his methods were working correctly. He really panicked when he obtained the first set of data from 51 Pegasi, because he was convinced there must be a bug in his analysis software. There was something wrong, because the measurements seemed far too good to be true. The problem was that the data were telling him a story that pointed very clearly to the presence of a planet, but this was not what he wanted or expected to see. He wanted the star to behave normally like all the other stars, so he could continue refining his technique and building up his data set without any controversial claims. He spent considerable time trying to debunk his own data, going back through his software line by line looking for errors that could explain away this anomalous signal. He checked and rechecked everything he could think of, but eventually, after exhausting all other possibilities, he had to admit to himself that he had tried everything he could to explain away the result, and nothing worked. The signal was real. It must be a planet. The thought was almost unbelievable. Could he really have found an exoplanet? In his excitement and disbelief, he sent a fax to Michelle Mayer, who was still on vacation in Hawaii. The fax said simply, "I think I have found a planet." This was not the kind of message that Mayer expected to receive while relaxing on a Hawaiian beach. The data indicated an object with approximately half the mass of Jupiter, orbiting the star with a period of just 4.5 days. This meant the planet was orbiting extremely close to its star, about 20 times closer than the distance between Earth and the Sun. At that proximity to the star, the planet would be extremely hot, with surface temperatures far exceeding anything in our solar system. After checking and rechecking the data repeatedly and confirming the reality of the signal, in October of 1995, the first exoplanet orbiting a sun-like star was officially announced to the world. When they went public with the discovery, Queloz remembered that nobody believed them at first. Many astronomers were highly skeptical of the claim. Scientists, who were graduate students at the time, remembered the announcement as an absolutely stunning moment. It was just such a crazy finding that was hard to accept, and the reason this discovery was so difficult for many astronomers to accept was that our own Jupiter takes nearly 12 years to complete one orbit around the Sun, but this newly discovered planet completed an entire orbit around its star in just a few days. Not only did we definitely not have any gas giants located so close to our Sun, but according to the prevailing theories of planet formation, planets simply could not form that close to a star. The intense heat and radiation near a star should prevent gas giant formation in such locations. So how could such a planet possibly exist? Asterisk if the signal really was indicating the presence of a gas giant planet so close to its star. That planet would have had to form somewhere else initially, far out from the star, where conditions were cooler and more conducive to gas giant formation. And then, somehow, it would have had to migrate inward over time. The planet must have interacted gravitationally with the disk of gas and dust from which it formed, or with other planets in the system, causing it to spiral inward toward the star over millions of years. Asterisk this inward migration would mean that the big planet had come spiraling in through the inner solar system, potentially destroying all the smaller rocky planets in its path. That was not supposed to happen according to our models of planetary system formation. The arrangement we see in our own solar system, with small rocky planets close to the sun and gas giants farther out, was thought to be the natural and perhaps universal result of planet formation. Asterisk this discovery meant that our solar system was actually quite different from what they were finding elsewhere. Other planetary systems could have radically different configurations, and that was indeed a tough pill to swallow for many astronomers who had built their careers on models of planet formation based entirely on our own solar system. Asterisk the astronomical community was absolutely convinced that a gas giant planet like Jupiter could only exist in the outer regions of a planetary system, far from the central star, where it is cold enough for ice and gas to accumulate into such massive worlds. So you have to imagine the shock of coming forward with the first planet ever discovered orbiting another sun-like star, which was already a world premiere achievement. But then the planet itself was not at all what anyone expected to find. It wasn't completely the wrong place according to all existing theories. Asterisk the claim was almost impossible for many scientists to swallow. The leap was just too radical a departure from accepted understanding, a resistance to the discovery proved futile when Queloz' breakthrough technique quickly led to the discovery of several more close-orbiting gas giants around other stars. These became known as hot Jupiters, a completely new category of planetary body that nobody had predicted should exist. Asterisk in the following months after the initial announcement, as more hot Jupiters were discovered, the reality of the achievement became undeniable. Hot Jupiters were real, and they forced astronomers to completely rethink their theories of how planetary systems form and evolve. Asterisk looking back on the discovery of 51 Pegasi b in 1995, it is clear that this was the moment when everything changed. In astronomy, Queloz and Mayer had kicked the door wide open to an entirely new field of research. At the time of the discovery, Queloz was very proud simply to demonstrate that his instrument could actually detect an exoplanet, if one existed. He thought this was a great achievement that would eventually, over many years, lead to a handful of detections. Asterisk, but he was very far from realizing just how quickly the field would explode. Eventually turned out to mean only about 6 months before multiple other hot Jupiters were being discovered by his technique and by other research teams who rushed to confirm and extend the findings. That moment in the mid-1990s truly was when everything changed in astronomy. Asterisk the discovery of exoplanets revealed that nature did not obey the neat laws and assumptions that astronomers had set for themselves based solely on studying our own solar system, and that realization was immensely exciting for the entire field. The detection of 51 Pegasi b really tilted over our perspective of our solar system as just one possible realization of what planetary systems can actually look like, rather than the universal template for all planetary systems. Asterisk, but beyond the scientific excitement, the discovery of 51 Pegasi b also triggered a more basic and profound human instinct. The main reaction that researchers received from the general public and from the media was not about the scientific implications or the methods of detection. Instead, people wanted to know immediately whether there was life on that planet. Could there be living organisms on this newly discovered world? Asterisk the idea of life beyond Earth is so profoundly connected to human culture and imagination that as soon as there was even the slightest hint of other worlds existing, people immediately began to dream about the possibility of life existing on those worlds. The fire of public imagination was ignited instantly. Asterisk inspired by the discovery of 51 Pegasi b and the hot Jupiters that followed, another young astrophysicist named Sarah Seeger decided to tackle the formidable challenge of searching for signs of life on exoplanets. Sarah had always loved imagining that there must be some kind of life out there, somewhere in the universe. In her heart, her ultimate goal was to help humanity find a planet that was just like Earth. complete with oceans and continents and breathable air. A world orbiting around a sun-like star, where life, as we know it, could flourish, astronaut Sarah focused her research on an intriguing idea that had been around for nearly a century. The atmospheres of planets, including exoplanets, could potentially contain chemical clues that point to biological processes occurring on the surface below. The search for life by studying atmospheric gases was not a new concept in principle, but applying it to exoplanets was revolutionary. Astronauts consider our own atmosphere here on Earth. It contains oxygen, which comprises about 20% of our atmosphere by volume. This high concentration of oxygen exists only because of the presence of plants, a photosynthetic bacteria that continuously produce oxygen as a byproduct of photosynthesis. Without these organisms constantly replenishing the atmospheric oxygen, chemical reactions would quickly remove the free oxygen from our atmosphere. Within a relatively short time on geological scales, perhaps a few million years, Earth's atmosphere would have no significant oxygen content at all. Asterisk the idea that an exoplanet's atmosphere might carry the chemical fingerprints of any life forms living on that planet was extremely attractive to astrobiologists. But putting that elegant theory into practice faced a major stumbling block. At the time in the late 1990s, nobody knew whether we could even detect exoplanet atmospheres at all, much less analyze their chemical composition in enough detail to search for biosignatures. The astronomy community was deeply skeptical and wanted to know why scientists like Sarah were even bothering to think about atmospheric analysis. After all, we could barely detect the planets themselves as tiny points of light. Why would anyone think we could study something as subtle as atmospheric composition? It seemed absurdly ambitious. Asterisk a crucial breakthrough came in 1999 when a hot Jupiter was detected using a different method than Queloz had employed. This planet was observed as it transited across the face of its star, meaning the planet passed directly between the star and Earth from our perspective, causing a tiny, temporary dimming of the starlight. Asterisk the transit method involves measuring the small dip in the intensity of starlight that occurs when a planet crosses in front of the star. The amount of dimming tells you about the size of the planet relative to the star. But the discovery of transiting exoplanets suggested an intriguing additional possibility. To Sarah Seeger, could the atmosphere of a transiting planet somehow leave its mark on the starlight passing through it? Asterisk Sarah's theoretical prediction was that gases present in the planet's atmosphere should leave their signature imprinted on the spectrum of starlight that passes through the atmosphere during a transit. Different molecules in the atmosphere would absorb light at specific characteristic wavelengths as the starlight passed through, leaving telltale gaps or absorption features in the spectrum. Asterisk by carefully comparing the spectrum of the star when it is observed by itself with the spectrum during a transit when the planet is in front of the star, astronomers should be able to pick out the absorption features caused by gases in the planet's atmosphere. It was a beautiful idea in principle, but would it actually work in practice? Asterisk the challenge was that the signal from the atmosphere would be incredibly tiny and difficult to detect. To understand the difficulty, think of the atmosphere surrounding a planet like the thin skin of an onion. Now imagine trying to see that onion skin silhouetted against a giant, brilliantly glowing backdrop. The atmosphere represents an incredibly small fraction of the total area of the planet, and the absorption it causes is correspondingly minute. Asterisk after years of developing her theoretical framework and working out the details of what should be observable, Sarah Seeger finally proved all the skeptics wrong in 2001, using space telescope observations. The element sodium was definitively detected in the atmosphere of a gas giant planet, located 159 light-years from Earth. Asterisk using Sarah's prediction and methodology, it was the first time ever that an exoplanet atmosphere had been observed, and had specific chemicals identified within it, and that was just an incredible, stunning, wow moment for everyone involved. The field of exoplanet atmospheric characterization was born. Asterisk the detection of sodium was quickly followed by discoveries of other elements and molecules in exoplanet atmospheres, including water vapor, which raised a tantalizing possibility. In the minds of many people, could a hot Jupiter potentially host living organisms? Asterisk for life as we know it to exist, liquid water is an absolute requirement. Every form of life on Earth depends on water as a solvent for the chemical reactions that sustain biological processes. so the detection of water in exoplanet atmospheres naturally sparked speculation about habitability. But unfortunately, the hot Jupiters where water was being detected were simply way too hot for liquid water to exist. These planets orbit so close to their stars that their surface temperatures are probably well above 1000 degrees Celsius. So yes, there's water present in hot Jupiter atmospheres, but it exists only as superheated steam, not as liquid water. The temperatures are far too extreme for water clouds to condense, much less for liquid water to pool on any surface. Which means, unfortunately, that there is essentially no chance that life could exist on hot Jupiters. The conditions are simply too hostile. These worlds are both exotic and deadly, fascinating to study, but completely inhospitable to any form of life we can imagine. But this raised an important question. Were hot Jupiters typical of all exoplanets, or were they just the easiest type to detect with our current methods, giving us a biased view of what exoplanets are really like? In the early 2000s, astronomers definitely had a very skewed and incomplete view of planets and planetary systems beyond our own solar system. The detection methods being used at the time could only find big planets, and specifically big planets orbiting very close to their stars. These were the easiest to detect because they produced the strongest observable signals. Gas giants like 51 Pegasi b were relatively easy to find using the radial velocity method. Because of their large mass and short orbital periods, their substantial gravitational pull on their parent star created easily detectable wobbles. And because they orbited so quickly, you could observe multiple orbits in a reasonably short observation campaign. But these same detection methods would completely miss any small, rocky, Earth-like worlds that might exist in these systems. Hot Jupiters are undeniably interesting from a scientific perspective. They challenged our theories and expanded our understanding of planetary physics. But if your goal is to understand whether life exists elsewhere in the galaxy, hot Jupiters are simply not the information you are seeking. To search for life, astronomers needed to find a different type of planet entirely. They needed to find worlds more similar to Earth, worlds with moderate temperatures where liquid water could exist on the surface. The search for exoplanets capable of sustaining life would require a different, more ambitious approach than had been attempted before. What was needed was a dedicated space mission specifically designed to find Earth-like planets. And one NASA scientist had been working on exactly such a concept for decades. On March 6, 2009, the Kepler Space Telescope launched from Cape Canaveral in Florida aboard a Delta II rocket. The launch was a moment of tremendous excitement and relief for everyone involved in the mission. Some of the scientists and engineers watching the launch could barely believe it was finally happening after so many years of proposals and setbacks. The Kepler mission was, in some ways, just a relatively small and focused mission that would poke its nose into one small corner of the galaxy and ask the fundamental question, what is out there? But in other ways, it represented an enormous gamble and a revolutionary approach to astronomy. The Kepler mission was the brainchild of NASA scientist Bill Brodsky, who had been advocating for this type of planet-hunting telescope since the early 1980s. Bill understood that if humanity wanted to explore the galaxy and eventually travel to the stars, we needed to prove ahead of time that most stars actually have planets orbiting them. If there were no planets out there, then there would be no destinations worth traveling to, and certainly no possibility of finding life elsewhere in the universe. Bill's plan for the Kepler mission was elegantly simple in concept, but extremely challenging in execution. The telescope would detect small exoplanets as they transited in front of their stars, not one by one as previous efforts had done, but on an absolutely incredible scale. The mission concept was to have an extremely wide field of view that could observe many, many stars simultaneously. The goal was to observe 100,000 stars all at the same time, continuously monitoring them for the telltale dimming that would indicate a planet crossing in front of the star. The enormous technological challenge was whether the instrument could detect the incredibly minute changes in brightness caused by a small planet transiting a star. When an Earth-sized planet passes in front of a sun-like star, it blocks only about 1 part in 10,000 of the star's light. Detecting such a tiny change in brightness is extraordinarily difficult, and the instrument had to be able to do this reliably across the entire field of view, containing 100,000 stars. Bill Brodsky had first pitched his scheme to NASA back in the 1980s. But at that time, the technology had essentially no chance of meeting the technical challenges. The detectors were not sensitive enough, computers were not powerful enough to process the data, and the attitude control systems needed to keep a telescope pointed with sufficient precision did not exist. When Bill Brudsky first proposed this seemingly crazy technique of looking for transiting planets on such a massive scale, the proposal was not really taken seriously by most of NASA's review panels. He had to fight for funding year after year, facing repeated rejections. Bill himself recalled that in 1983, he would walk into NASA headquarters trying to convince administrators that they needed to fund this mission, and according to Bill, the program officers would practically hide in their offices or under their desks because they knew he was coming, and they did not want to face another one of his passionate presentations about planet hunting. Looking back on his experience, Bill Brudsky proved to be one of the most tenacious and dedicated scientists in the field. He never gave up on his vision despite facing rejection after rejection. If you are in the space exploration business, you need to be prepared for the long haul. Building a space mission from initial concept to launch typically takes at least a decade and often much longer. But NASA was never going to invest $400 or $500 million in a mission unless they knew for certain that the technology would work and that planets were actually out there to be found. The discovery of 51 Pegasi b in 1995 was a turning point that helped change NASA's attitude. This discovery finally encouraged NASA to take a serious chance on Bill's mission concept. Up until the mid-1990s, people had speculated and theorized that there must be planets around other stars, but nobody had any solid empirical proof. The fact that Queloz and Mayer had made a definitive detection added crucial scientific credibility to the idea of exoplanet research. If planets were really out there, then maybe it was worth investing in a mission to find them systematically. 25 years after Bill Brudsky first conceived of his planet hunting mission, the Kepler Space Telescope was finally ready to begin its search for Earth-like exoplanets. Positioned far above Earth's atmosphere in a heliocentric orbit, the telescope would enjoy a crystal-clear view of the stars that ground-based astronomers could only dream of achieving. There would be no atmospheric turbulence to blur the images, no day-night cycle to interrupt observations, no clouds or weather to interfere. The mission was either going to be brilliantly successful or a complete failure. Nothing quite like it had ever been attempted before in the history of astronomy. But finally, after all the years of planning and development, Kepler opened its eye to the cosmos and looked at the stars. There were tens of billions of stars shining in the Milky Way, and Kepler was now watching 100,000 of them. Simultaneously, it was a beautiful sight for the mission team. Within just a few hours of beginning observations, the data streaming back from Kepler showed that one of the stars that astronomers already knew had a planet was showing a transit signal. An exoplanet located an incredible 750 light-years from Earth was detected passing in front of its star, causing the expected dimming of starlight. This told the mission team that the instrument was working exactly as designed. They were absolutely delighted, just ecstatic with this early confirmation that their techniques were sound. Finding an exoplanet that you already know about might seem like a modest achievement, but it was crucial for validating the mission. Now they knew for certain that Kepler could detect the subtle signals they were looking for. But Bill Brudsky's sky survey was still an enormous gamble in terms of what it would actually discover. The transit technique only works when a planet happens to be orbiting in exactly the same geometric plane that we are viewing from Earth. If the planet's orbit is tilted even slightly with respect to our line of sight, we will never see it pass in front of its star. This geometric constraint means that you are basically eliminating 99% of all planets from potential detection. You can only see the ones whose orbits happen to be aligned just right. But even with this severe geometric limitation, there were so many stars being monitored by Kepler that the transit technique was finding dozens and dozens of new exoplanets. In short order, the key to success was a massive scale of the survey. By watching 100,000 stars continuously, Kepler was bound to catch those relatively few systems where the orbital alignment was favorable for transit detection. The Kepler spacecraft was designed to be, in many ways, the most boring mission that had ever been built. All it did was take picture after picture after picture of the exact same field of view, capturing a new image every 6 seconds, the same 150,000 square degrees of sky. The same 100,000 stars over and over again, day after day, month after month. The telescope never moved to point at new targets, never changed its observing strategy. It just stared at the same patch of sky with unwavering attention, looking for tiny periodic dips in starlight. Asterisk, at the core of the Kepler mission was Bill Brudge's deep desire to find Earth-like planets located in the habitable zone of their stars. This habitable zone is also sometimes called the Goldilocks zone, the region around a star that is neither too hot nor too cold for liquid water to exist on a planet's surface. It is the zone where conditions are just right for life as we know it to potentially thrive. Asterisk, the mission parameters were tuned very, very carefully with this goal in mind. The focus was specifically on finding Earth-like planets in the habitable zones of sun-like stars where water could exist in liquid form on the surface. This was the holy grail of exoplanet research, the ultimate goal that would tell us whether worlds truly similar to our own Earth exist elsewhere in the galaxy. Asterisk, for Kepler to confirm the detection of an Earth-like planet in an Earth-like orbit, the mission needed to observe 3 or 4 complete transits of that planet across its star. Since an Earth-like orbit takes 1 year, this meant Kepler needed to operate successfully for at least 3 to 4 years minimum to catch enough transits to confirm the most Earth-like planets. This was built into the mission design from the beginning. Asterisk, the whole mission concept was so fundamental and groundbreaking because Bill Brudge was not just trying to detect any planets at all, but rather was specifically trying to find that special subset of planets that existed in the habitable zone where life might potentially have appeared and evolved. Asterisk, at NASA's Ames Research Center, where the Kepler mission was managed, they set up a display in the lobby of the main administrative building. This display had digital counters that would show visitors how many exoplanets had been discovered by Kepler, and how many of those exoplanets had been discovered in the habitable zone of their stars where life might exist. Asterisk, these numbers began to grow and grow and grow as the mission progressed. The discoveries were coming in so fast that suddenly the mission team discovered they did not have enough digits on their display counters to encompass all the planets that were being discovered. They had to upgrade their displays to handle the flood of new worlds being found. Asterisk, after 4 years of staring continuously into the Milky Way, monitoring the same 100,000 stars night after night without pause, Bill Brudge and his team were ready to reveal their top picks from the hundreds of confirmed planets discovered so far. They held a press conference to announce what they considered the most exciting and significant discoveries. Asterisk, Bill Brudge announced that they had found a planets located in the habitable zone of another star, and these were the best candidates for potentially habitable worlds that had been found to date. These planets might have the possibility of liquid water on their surfaces, which was incredibly exciting news for the search for life beyond Earth. Asterisk, located more than 1,200 light-years away from Earth, the most Earth-like of these 2 planets was designated Kepler 60F. The data from the Kepler telescope suggested this world could potentially be a water world, a planet completely covered by a vast global ocean with no continents or exposed land masses. Asterisk, the reason that astronomers referred to it as potentially a water world was because, given the planet's calculated mass and radius derived from the transit observations, it could in fact harbor a huge envelope of water on its surface. If the planet formed in a region rich in ice that subsequently melted as the planet migrated to its current orbit, it could have accumulated enough water to cover the entire surface to great depth. Scientists speculated that all sorts of life could potentially exist in such a global ocean. Could there be an ecosystem with small creatures and larger fish to eat them, and those fish developing strategies to avoid being eaten in turn? Perhaps there could even be organisms that learn to propel themselves out of the water briefly, like the flying fish we have in Earth's oceans. The possibilities for biological diversity in such an environment were fascinating to contemplate. Asterisk, the discovery of Kepler 6F was certainly a high point for the mission and for Bill Brudge personally. The team was absolutely delighted to find this potentially habitable world, as were their sponsors at NASA headquarters who had funded the mission. It seemed like the mission was achieving exactly what it had set out to do, and there were hopes for even more dramatic discoveries to come. Asterisk, but behind the scenes, unknown to the public and the media celebrating these discoveries, the Kepler mission was facing a serious crisis that threatened to end operations prematurely. The telescope's ability to stare continuously at the same patch of sky depended critically on a guidance system that used for gyroscopic stabilizers, called reaction wheels. These reaction wheels were the key to Kepler's precision. The guidance system was so incredibly precise that the image of the same star would fall on the exact same pixel of the detector month after month, with almost no drift or movement. This precision was essential for detecting the tiny brightness changes caused by transiting planets. But in 2013, 2 of the 4 reaction wheels failed mechanically. This was a catastrophic failure in terms of the original mission plan. The failures meant that Kepler could no longer maintain its precise pointing. At the original field of view, the telescope hardware still worked perfectly, but without enough functional reaction wheels, they could not keep it pointed in the right direction anymore. It was a really tense period for everyone involved in the mission. Many people thought the mission was finished. The general feeling was that Kepler had had a good run and had collected a tremendous amount of valuable data, but now it was done, without the ability to point accurately. How could observations continue? But Bill Brutsky was not ready to give up yet. Perhaps there was some way the mission could be salvaged and extended even with only 2 working reaction wheels. The team sent out an urgent call for help to the broader aerospace engineering community, essentially broadcasting a plea saying, "Help, help, we need creative solutions to this problem." All spacecraft in our solar system experience a subtle but constant force from sunlight itself. Photons of light carry momentum, and when they strike a surface, they exert a tiny push. This phenomenon is called solar radiation pressure. Some clever engineers pointed out that perhaps this solar pressure could be used as a substitute for one of the failed reaction wheels. The engineering team came up with an ingenious idea. They suggested that if they oriented the spacecraft correctly, they could use the pressure from sunlight as a stabilizing force. We have got to functioning reaction wheels remaining, and we have the sun constantly pushing on the spacecraft. If we arrange the orientation so that the sun's push acts like one of the wheels, we might be able to maintain pointing after all. To give you a sense of how delicate this solution was. Each square meter of a satellite like Kepler experiences solar radiation pressure equivalent to the weight of a single grain of salt here on Earth. That is an incredibly tiny force, but the engineers hoped that even this minuscule push from sunlight, properly exploited, would be enough to stabilize the drifting telescope and allow it to continue making observations. It was an extremely clever idea, using the very pressure of radiation from the sun as a countervailing force to maintain stability. This would extend the operational life of the mission and allow the collection of even more valuable data. The ingenious fix turned out to be successful. The Kepler team managed to stabilize the telescope using the 2 remaining reaction wheels, plus solar pressure, which was a remarkable achievement of engineering creativity. However, this jury-rigged pointing system could only stabilize the telescope for much shorter periods than the original 4-wheel system had allowed. There were definite consequences for the mission's scientific goals. With the new constraints, Kepler could still find exoplanets with short orbital periods, such as giant planets that complete an orbit in just 1 or 2 transits. But the modified mission could not continue the original objective of finding true Earth analogs with year-long orbital periods. To confirm an Earth-like planet in an Earth-like orbit, you need to observe for several years to catch multiple transits and rule out other explanations for the brightness variations. The modified Kepler mission simply did not have enough stable pointing time to accomplish this anymore. They needed more time to find those possibly true Earth analogs, and that time was no longer available. On October 30th, 2018, after more than 9 years in space, the Kepler Space Telescope finally ran out of the fuel needed to maintain its orientation and downlink data to Earth. The mission was over. For those who had worked on Kepler for decades, it was an emotional moment, but also a celebration of what had been accomplished. The mission had definitely accomplished its primary objective and far exceeded initial expectations. So while it was sad to see the spacecraft shut down, there was also satisfaction that it had completed its job successfully. The Kepler mission ultimately discovered more than 2,600 confirmed exoplanets, with several hundred of those located in the habitable zones of their stars. This was an extraordinary achievement that revolutionized our understanding of planetary systems. But perhaps the real surprise from the Kepler mission was not just the number of planets found, but the incredible diversity of worlds revealed by the data. Kepler found so many new types of planets that had never been imagined before. It really opened astronomers' eyes to the full range of possibilities. The planetary systems discovered by Kepler were not like our solar system at all in many cases. Some systems had giant planets where we have small planets in our solar system. There were giant planets much larger than Jupiter, and tiny little planets apparently disintegrating as they orbited close to their stars. The variety was astonishing and completely unexpected. Kepler really demonstrated that there exists an interstellar zoo of planetary worlds out there. The types of exoplanets that exist throughout the galaxy are really limited only by our imagination, and sometimes they even exceed what we thought was possible. At NASA's Jet Propulsion Laboratory in California, scientists use observational data from surveys like Kepler, along with sophisticated computer models to simulate the actual conditions that might exist on some of these extraordinary worlds in the cosmic zoo. This work involves taking whatever data is available from telescopes, and then using scientific understanding plus imagination to try and figure out what the weather patterns and atmospheric conditions might actually be like on these distant worlds. The ultimate goal is to really start to narrow down the question of whether life might exist on any of these planets. The number crunching and computer modeling have led to some absolutely astonishing conclusions about the nature of some exoplanets in our cosmic neighborhood. Consider the exoplanet designated 55 Concrete E. What makes this planet particularly interesting is not just that it is a fascinating world, but also the fact that we can actually see its parent star with the naked eye from Earth. If you know where to look, this planet is orbiting a star that is visible without a telescope. Located just 40 light years away, the planet itself, designated 55 Concrete E, is approximately twice the diameter of Earth, so it is classified as a super-Earth. But any similarity to our homeworld ends there. This planet exists in an absolutely ridiculously close orbit around its star. The orbital period is less than a day, which means the planet whips around its star at incredible speed, staying perpetually close to the stellar surface, because of this extreme proximity to its star. Surface temperatures on 55 Concrete E are calculated to be well above 1000 degrees Celsius, or over 2000 Kelvin if you are using the scientific temperature scale. When planetary scientists think about 55 Concrete E, the dominant feature that comes to mind is lava. The surface must be covered in oceans of molten rock, at such extreme temperatures. None of the solid materials that make up a rocky planet can remain solid. Everything melts. The entire surface would be a churning sea of molten rock, with temperatures hot enough to melt iron, silicon, and virtually every other component of a terrestrial planet, but it gets even stranger. The heat is so intense that the molten rock cannot remain liquid either, at least not on the hottest parts of the planet. Some of the lava would actually vaporize, creating a bizarre atmosphere composed of gaseous rock, or what scientists call a silicate vapor atmosphere. This is not water vapor or nitrogen or oxygen like Earth's atmosphere, but rather vaporized rock floating above a molten surface. On the backside of the planet, the side facing away from the star where temperatures are marginally lower, it is theoretically possible that this gaseous rock atmosphere could cool enough for the silicon vapor to condense back into droplets. If this happens, then it would literally rain rocks on 55 Concrete E. Droplets of molten rock would fall from the silicate vapor clouds back down to the magma ocean surface. This is a very weird atmospheric scenario that has no parallel anywhere in our solar system. Despite these apocalyptic conditions that would instantly vaporize any spacecraft or probe we could send there, this nightmarish world could actually be the most precious and valuable exoplanet yet discovered, at least in terms of material composition. If you analyze the chemical composition of the star that 55 Concrete E orbits, you find that this star is significantly more carbon-rich than our Sun. This has important implications for any planets that form from the same disk of material around this star. In our solar system, oxygen is more abundant than carbon, which leads to the formation of silicate rocks. But in a planetary system where carbon is more abundant than oxygen, as appears to be the case for 55 Concrete, the chemistry works very differently. Scientists believe that 55 Concrete E might actually be what is called a carbon planet. In such a world, instead of being made primarily of silicate rocks like Earth, the planet could have a composition dominated by carbon compounds. Under the intense pressure and temperature conditions inside such a planet, there could be a layer, or region deep within the planet's interior where pure carbon exists in the form of diamond. Asterisk, in other words, 55 concrete E might have massive quantities of diamond in its interior, perhaps even an entire layer of solid diamond underneath the lava surface. These are real places that exist in our universe. We can point telescopes at them and say with confidence that this is indeed a planet, where it might rain molten rock from clouds of vaporized silicon, or which might have a diamond layer beneath its hellish surface. Asterisk, these are not science fiction fantasies, but actual worlds that exist in our universe. Places that we can study and characterize even though we cannot visit them directly. The exoplanet 55 concrete E represents a nightmare world where life would be utterly impossible. But in 2017, astronomers discovered an equally bizarre but completely different planetary system located at roughly the same distance from Earth that offers much more hope for habitability. Asterisk, the TRAPPIST-1 system, named after the telescope that discovered it, is comprised of 7 closely packed planets that are all roughly similar in size to Earth. These planets orbit what astronomers classify as an M-dwarf star, also called a red dwarf, which is much smaller and cooler than our Sun. Asterisk, the TRAPPIST-1 system is exciting for astronomers because, in some ways, it resembles a scaled-down version of our own solar system. It has a whole collection of multiple planets rather than just 1 or 2, and remarkably, 2 or 3 of these planets appear to be located in a habitable zone, where temperatures could allow liquid water. This is incredibly exciting because it represents a planetary system that matches the model that astronomers had long theorized might exist around other stars. Asterisk, the star at the center of the TRAPPIST-1 system is a much cooler, redder, and physically smaller star than our Sun, because the star is smaller and dimmer. The entire planetary system is tucked in much closer to the star than the planets in our solar system are to the Sun. Despite being closer, the planets receive roughly the same amount of heat and light because their star is so much dimmer than our Sun. The innermost planets in the TRAPPIST-1 system orbit at distances that would place them inside the orbit of Mercury in our solar system, yet they may have temperatures similar to Earth. Asterisk, this compact mini-solar system could potentially have liquid water oceans on some of its planets. The orbital configuration and dynamics of the system indicate that the planets likely migrated inward from locations farther from their star originally. This migration history is important because it means the planets had the opportunity to accumulate substantial amounts of ice during their formation in the colder outer regions of the system. This ice would have subsequently melted as the planets moved into their current orbits, closer to the star, potentially creating planets with enormous amounts of surface water. Asterisk, if it were somehow possible for a human to stand or float on the surface of one of the TRAPPIST-1 planets, assuming they had a spacesuit or breathing apparatus, they would see a sky very different from what we see on Earth. The star would appear much closer in the sky than our Sun appears from Earth, but it would also be significantly dimmer and distinctly redder than our yellow Sun. Asterisk, but perhaps most spectacularly, you would not just see a moon in the sky like we do from Earth. Instead, you would see neighboring planets visible as large disks in the sky, much larger and more prominent than any moon, because the 7 planets are packed so close together in their orbits. When they are properly aligned, one planet would be able to see one or more of its siblings as prominent features in the sky. Asterisk, everything that we would perceive with our human eyes on a TRAPPIST-1 planet would have a distinctly red tint to it, because the star emits primarily red wavelengths of light. Objects that appear green here on Earth under our yellow Sun would appear quite different there. Plants with green leaves, if any photosynthetic life evolved on such a world, would actually appear black or very dark to our eyes rather than green, because they would be absorbing the red light rather than reflecting green light as Earth plants do. Asterisk, everything about the TRAPPIST-1 system is exotic compared to our solar system, yet it also feels oddly familiar in its overall structure. The system demonstrates that planetary systems can be scaled versions of the same basic architecture, just adapted to different types of stars. Asterisk, dwarf stars like TRAPPIST-1 are so intrinsically dim that they are completely invisible to the naked eye when viewed from Earth, even though many of them are relatively nearby in cosmic terms. But despite being dim, these red dwarf stars are actually the most common type of star in the entire galaxy. They outnumber Sun-like stars by a ratio of approximately 10 to 1. Asterisk, this statistical fact has profound implications for the search for life in the galaxy if red dwarf stars are the most common type, and if they routinely host these compact systems of potentially habitable planets. As TRAPPIST-1 suggests, then the majority of stars in our galaxy might have these miniature solar systems with Earth-sized planets in habitable zones. The potential for life-bearing worlds becomes much greater when you consider that the most numerous type of star might be capable of hosting habitable planets. Asterisk, the TRAPPIST-1 system offers a recognizable template for how life might arise on worlds quite different from Earth, but still potentially hospitable. But could observations of the very nearest star to our own sun suggest that we already have neighbors even closer than TRAPPIST-1? Asterisk, the closest star system to our sun is the Alpha Centauri system, and the nearest individual star is Proxima Centauri, a red dwarf located just over 4 light years away. In 2016, astronomers announced the discovery of a planet orbiting Proxima Centauri, designated Proxima Centauri b. Asterisk, Proxima Centauri b has captured tremendous public and scientific imagination because it is literally one of the closest exoplanets we could possibly investigate. It is only 4 light years away, which is practically next door in cosmic terms. Additionally, the planet appears to be located in a habitable zone around its star, meaning it is heated by the star to temperatures that should be roughly compatible with liquid water existing on the surface. Asterisk, this all sounds very positive and promising for the potential habitability of Proxima Centauri b. But then the situation gets considerably more weird and complicated when you examine the details more carefully. Asterisk, based on the planet's orbital characteristics, astronomers believe that Proxima Centauri b is probably tidally locked to its star, similar to how our moon is tidally locked to Earth. Tidal locking means that one hemisphere of the planet permanently faces the star, experiencing eternal daylight, while the opposite hemisphere faces away from the star in perpetual darkness and cold. Asterisk, this raises fascinating questions about whether such a world, split between permanent day and eternal night, could ever develop or support life. Could life exist in such an extreme environment with no day-night cycle and such dramatic temperature differences between hemispheres? Asterisk, scientists who model the climate of Proxima Centauri b think that any water on the planet would probably tend to migrate to the night side and freeze solid there. The daylight side would be too hot for ice, while the night side would be too cold for liquid water. Over time, water vapor would gradually migrate through the thin atmosphere from the hot side to the cold side, where it would freeze and accumulate as ice. Asterisk, but there is a potentially habitable middle ground. As ice accumulates on the night side, the edges of the ice sheet would naturally creep toward the day side due to glacial flow and sublimation. As this ice approaches the boundary between day and night, it would begin to melt. Scientists refer to this boundary zone as the terminator or the terminator zone, which is the transition region between the bright day side and the dark night side of a tidally locked planet. The conditions in this twilight zone might be just right for life to have formed and persisted. There could be a habitable ring around the entire planet where temperatures are moderate and liquid water can exist. Even though both the day side and night side are inhospitable, asterisk, any organisms living in this terminator zone would have to deal with the additional challenges and perils of being so close to their parent star. Proxima Centauri, though it is the smallest and dimmest type of star, is a particularly volatile example of a red dwarf. At less than 5 billion years old, Proxima Centauri is actually very young for a red dwarf star, which can live for trillions of years, and young red dwarfs are known to be prone to violent outbursts. Asterisk, when a red dwarf is young and active, it emits tremendous amounts of high-energy radiation, including frequent powerful stellar flares. These flares are much more intense than anything our sun produces. The planet orbiting so close to its star would be regularly blasted with intense radiation. From these flaring events, asterisk, Proxima Centauri b is probably getting hit by major stellar flares every week or even more frequently, which would seem to make the surface extremely hostile to life. But interestingly, scientists are not overly worried that the flares would necessarily kill all life on the planet. Life is remarkably resilient and adaptable. There is always the dark side of the planet where organisms could shelter from the worst radiation. There are always the oceans, if oceans exist, where water would provide shielding from radiation. So life itself would probably not be entirely sterilized by the flaring activity. Asterisk, the stellar flares would certainly create a very tricky and challenging landscape for life. requiring adaptations to cope with periodic radiation exposure, but it would not necessarily be a complete barrier to the existence of life. Asterisk, the violent stellar activity might also create some spectacular celestial light shows. For any organisms brave enough or adapted enough to exist on the surface during a flare event, it is quite possible that there would be periodic transfers of high-energy charged particles from the star to the planet, similar to what happens when solar wind particles from our sun interact with Earth's magnetic field. This could create aurora, the northern and southern lights that we see on Earth, except potentially much more intense and possibly ever present on Proxima Centauri b. Asterisk, so the ultimate question is, could Proxima Centauri b potentially be a home away from home for life, or even eventually for human colonization? Well, Proxima Centauri b holds the distinction of being the closest known exoplanet to Earth, located in the very nearest star system to our own. It is one of the first places that humankind will seriously consider exploring if we ever develop the technology for interstellar travel. Asterisk, in Proxima Centauri b, we might discover that Earth really does have a kind of twin in the cosmos, though perhaps not an identical twin. It would be more like a fraternal twin or a distant cousin. A world that shares some characteristics with Earth, but also has its own unique and exotic features, shaped by its very different stellar environment. Asterisk, the progress that has been made in exoplanet research over the past few decades is absolutely staggering when you step back and consider the big picture. Today we take it for granted that there are thousands of known exoplanets orbiting stars throughout our region of the galaxy. We hear about new discoveries regularly, and they barely make headlines anymore unless there's something particularly unusual about the planet. Asterisk, and yet it is worth remembering and appreciating that only a few decades ago, at the end of the 20th century, we had not definitively observed even a single exoplanet. The entire field has emerged and matured within a single human generation. Asterisk, less than 40 years after Richard Terrell photographed the fuzzy debris disk around Beta Pictus. Using his improvised coronagraph, astronomers released absolutely astonishing footage showing an actual exoplanet visibly orbiting the same star over time. The planet, designated Beta Pictus b, can be seen moving in its orbit in time-lapse imagery constructed from observations spanning several years. Asterisk, we have come so far from those early crude images captured through a makeshift coronagraph to actually seeing an exoplanet orbiting its star in real-time observations. It is very exciting to see that progression, to witness that evolution of our knowledge and technological capabilities happening within a single human lifetime. Asterisk, Beta Pictus b itself is classified as a super Jupiter because it is significantly more massive than our own Jupiter. Using spectroscopic observations, astronomers have even been able to measure the rotation rate of this distant planet, determining how fast it spins on its axis. The rotation period and other characteristics suggest that Beta Pictus b might actually resemble Jupiter in some ways, potentially featuring bands of clouds and massive vortices rotating in its thick atmosphere. Asterisk, for Richard Terrell, who photographed the first image of the debris disk around Beta Pictus back in 1984, the subsequent discovery of actual planets in that system represents a remarkable vindication of his early work. He and his colleagues were the first people to see evidence of that planetary system forming, and now it has been added to the catalog of confirmed planetary systems. Part of the growing interstellar zoo of worlds. Asterisk, it is certainly a great accomplishment to have on your scientific resume, being part of the team that took the first image hinting at the existence of planets around another star. Asterisk, every advance in technology over these past few decades has added new layers of detail and understanding to the exoplanet story. The capabilities of our telescopes and detectors have grown exponentially, allowing us to not just detect planets, but to characterize their properties in ever greater detail. But despite all this remarkable progress, we still must ask ourselves the fundamental question that drives so much of this research: are we any closer to actually finding life beyond Earth? Asterisk, are we at the cusp of discovering life today? Scientists working in the field would honestly say no, we are not quite there yet. But the important point is that we now have a clear roadmap for how to get there. We know what we are looking for. We understand what biosignatures might look like, and we are actively developing the technology and missions that will allow us to search for those traces that could constitute evidence of life on other worlds. Asterisk, when we look at the space missions that are currently being planned and developed for the coming decades, We see designs for truly enormous telescopes that will be capable of directly imaging exoplanets and analyzing the light from their atmospheres in unprecedented detail. These future observatories will be able to see what chemicals and molecules are present in exoplanet atmospheres. They will search for combinations of gases that might indicate biological processes, signs of life that could definitively answer the age-old question of whether we are alone. Some of these planned missions might even be capable of directly imaging the surfaces of nearby exoplanets, potentially seeing continents, oceans, clouds, and other features. While we do not know for certain whether life exists elsewhere, scientists do not feel the need to engage in endless speculation about it. The great thing about astronomy as a scientific discipline is that it will not be very long before we have much better observational data and more definitive answers. All of our current speculations and dreams about what might exist on other worlds will soon be tested against actual observations. We will be able to see which of our predictions and theories correspond to reality, and which ones need to be revised or discarded entirely. The evidence will tell us the truth, one way or another. The universe has already proven to be far more exciting, diverse, and surprising than it was 40 years ago, when our imaginations could not even comprehend the different types of planetary environments that actually exist. Our pre-discovery assumptions about planetary systems were remarkably narrow and parochial, based entirely on our experience with our own solar system. But the future promises to be even more exciting than the present. The journey of exoplanet discovery has really consisted of two major phases so far. The first phase, which we have now largely completed, was simply finding planets and proving that they exist. This was the fundamental breakthrough that opened up the entire field. The next phase, which we are now entering, is finding life itself, or at least finding strong evidence that life exists or has existed on other worlds. This transition from planet detection to life detection represents one of the most profound scientific endeavors in human history. If we succeed in finding evidence of life beyond Earth, it will fundamentally transform our understanding of our place in the cosmos and answer questions that philosophers and scientists have been asking for thousands of years. Consider for a moment what we have learned in just the past 3 decades. We have discovered that planets are not rare, special objects found only around our sun, but rather common features of the galaxy. Current estimates based on Kepler data and other surveys suggest that virtually every star in the Milky Way likely hosts at least one planet. With approximately 200 billion stars in our galaxy, that implies the existence of hundreds of billions of planets in the Milky Way alone. Furthermore, we have learned that a substantial fraction of these planets, perhaps 20% or more, exist in the habitable zones of their stars where liquid water could exist on the surface. This means there could be tens of billions of potentially habitable worlds in our galaxy alone, and our galaxy is just one of hundreds of billions of galaxies in the observable universe. The sheer scale of these numbers is staggering, even if the emergence of life is an extremely rare and improbable event, requiring very specific conditions and an extraordinary sequence of chemical accidents. The number of potential sites where it could occur is so vast that life might still be relatively common in the universe as a whole. We have also learned that planetary systems exhibit extraordinary diversity. There is no single template for how a planetary system must be organized. We have found systems with hot Jupiters hugging their stars in impossibly tight orbits. We have found systems like TRAPPIST-1 with multiple Earth-sized planets packed closely together. We have found planets orbiting binary star systems, worlds that would see 2 suns rising and setting in their skies, like the fictional planet Tatooine from Star Wars. We have found rogue planets drifting through interstellar space with no star at all, ejected from their original systems and condemned to wander the galaxy alone in darkness. The catalog of planetary types has expanded far beyond what anyone imagined possible. There are the super-Earths, rocky planets larger than Earth but smaller than Neptune, a category that does not exist in our solar system but appears to be extremely common throughout the galaxy. There are the hot Jupiters that started this whole field of study. There are ice giants, lava worlds, water worlds, and planets we still cannot fully categorize because they are unlike anything in our experience. Each new type of planet discovered expands our understanding of planetary formation and evolution. Each discovery reveals new physical and chemical processes at work, new ways that matter can arrange itself under different conditions of temperature, pressure, and composition. The universe is teaching us that nature is far more creative and inventive than we ever gave it credit for. Asterisk as our technology improves, we are moving beyond simply detecting planets and measuring their basic properties like size and orbital period. We are now able to probe their atmospheres, determine their compositions, measure their temperatures, and begin to understand their weather patterns and climate systems. For the brightest and most favorable targets, we can even create crude maps showing how temperature and cloud cover vary across the planets. Surfaced asterisk the James Webb Space Telescope, launched in late 2021, represents the current state of the art in exoplanet atmospheric characterization. This enormous infrared observatory, with a mirror over 6 meters in diameter, is capable of detecting and analyzing the faint infrared light from exoplanet atmospheres. With unprecedented sensitivity and precision, early results from Webb have already revealed the atmospheric compositions of several exoplanets in remarkable detail, detecting water vapor, carbon dioxide, methane, and other molecules. Asterisk, but James Webb is just the beginning. Future missions currently in planning stages will be even more capable. The Nancy Grace Roman Space Telescope, scheduled for launch in the late 2020s, will use advanced coronagraph technology to directly image exoplanets that are currently too faint to observe. The European Space Agency's Plato mission will search for Earth-like planets around nearby stars. And looking further ahead, NASA and other space agencies are studying concepts for truly massive space telescopes that would dwarf even James Webb, with mirrors tens of meters across capable of directly imaging Earth-sized exoplanets and searching their atmospheres for biosignatures. The search for biosignatures, chemical signs of life in exoplanet atmospheres, has become one of the hottest topics in astrobiology. Scientists have identified several gases that could serve as potential indicators of biological activity. Oxygen is the most obvious example, since Earth's oxygen-rich atmosphere is maintained almost entirely by photosynthetic life. The simultaneous presence of oxygen and methane would be particularly intriguing, since these gases react with each other and would quickly disappear from an atmosphere, unless something was continuously replenishing them, potentially biological. Metabolism. Other potential biosignatures include more exotic molecules like dimethyl sulfide, which on Earth is produced primarily by marine phytoplankton, or phosphine, which can be produced by anaerobic bacteria. The challenge is that some of these molecules can also be produced by non-biological processes under certain circumstances. So detecting a potential biosignature gas would not be definitive proof of life. It would be tantalizing evidence requiring further investigation and confirmation through multiple independent lines of evidence. Asterisk scientists are also developing the concept of looking for technosignatures, rather than just biosignatures. While biosignatures would indicate the presence of any form of life, even microbial life, technosignatures would specifically indicate the presence of technological civilizations, capable of modifying their environment in detectable ways. This could include things like artificial lights on the night side of a planet, industrial pollutants in the atmosphere like chlorofluorocarbons that do not occur naturally, or even megastructures built around stars to harvest energy, sometimes called Dyson spheres or Dyson swarms. Asterisk the search for technosignatures builds on a decades-long SETI program, the search for extraterrestrial intelligence, which has been listening for artificial radio signals from other civilizations since the 1960s. While SETI has not yet detected any confirmed alien transmissions, the search continues and expands to new wavelengths and new search strategies. The discovery of thousands of exoplanets has given SETI researchers specific targets to focus on rather than just blindly searching the sky. Asterisk one of the most profound implications of exoplanet research is what it tells us about the potential longevity and fate of civilizations. By studying how planetary systems evolve over billions of years, how planets lose their atmospheres, how stars change as they age, we can begin to understand the lifetime of habitable conditions on various types of worlds. This has implications for understanding not just where life might exist now, but where it might have existed in the past or where it might arise in the future. Asterisk for instance, red dwarf stars like Proxima Centauri and TRAPPIST-1 have lifetimes of trillions of years, vastly longer than the 10 billion year lifetime of sun-like stars. This means that planets around red dwarfs could potentially remain habitable for extraordinary spans of time, giving life a much longer window to arise and evolve. On the other hand, red dwarfs go through a very active and violent youth lasting billions of years, during which they blast their planets with intense radiation and stellar flares that could strip away atmospheres and sterilize surfaces. The question of which factors dominate, the advantage of a long stable lifetime or the disadvantage of a violent youth, is still being debated and studied, but it has important implications for where we should focus our search for life. Should we concentrate on planets around sun-like stars, which offer more benign conditions but shorter habitable lifetimes? Or should we focus on the much more numerous red dwarf systems, which might ultimately host the majority of life in the galaxy? If planets that can survive the early bombardment of radiation? Another fascinating area of research involves understanding how common Earth-like planets actually are. The Kepler mission provided a statistical sample that allows astronomers to estimate the frequency of various types of planets based on Kepler data. Scientists have calculated what they call at Earth, the fraction of sun-like stars that host an Earth-sized planet in the habitable zone. Current estimates put at Earth at somewhere between 10 and 50%, meaning that perhaps 1 in 5 to 1 in 10 sun-like stars has a potentially habitable Earth-sized planet. This is an extraordinary finding with profound implications. It means that the nearest Earth-like planet in the habitable zone of a sun-like star could be as close as 10 or 12 light-years away. There could be dozens or hundreds of such worlds within 100 light-years of Earth. Some of these worlds might be visible to the naked eye as part of well-known constellations, hosting biospheres and perhaps even civilizations, while appearing to us as simple points of light in the night sky. The field of exoplanet research has also sparked renewed interest in interstellar travel and exploration for decades. The idea of sending probes to other star systems seemed like pure science fiction, an impossible dream given the vast distances and energy requirements involved. The nearest star system, Alpha Centauri, is over 4 light-years away, which means traveling at the speed of our fastest current spacecraft. It would take tens of thousands of years to reach, but the discovery of potentially habitable planets around nearby stars, including Proxima Centauri b, has motivated serious scientific and engineering studies of how we might realistically send probes to these systems within a human lifetime. Projects like Breakthrough Starshot are investigating the possibility of using powerful ground-based lasers to accelerate tiny ultralight probes to a significant fraction of light speed, perhaps 20% of the speed of light. At such velocities, a probe could reach Alpha Centauri in about 20 years. Such probes would necessarily be very small and simple, perhaps nothing more than a computer chip with a camera and radio transmitter attached to a light sail, but they could return the first close-up images and data from another planetary system. The technological challenges are immense, but they appear to be within the realm of what might be achievable with focused effort and investment over the coming decades. The broader cultural impact of exoplanet discoveries has been significant as well. The realization that planets are common throughout the galaxy, that many of these planets are potentially habitable, and that we might be able to detect signs of life on them within our lifetimes, has reinvigorated public interest in space exploration and astronomy. It has also sparked important philosophical and theological discussions about the implications of discovering life elsewhere. How would the confirmation that we are not alone in the universe affect human society? Would it unite us in the realization that we are all one species, sharing one small world in a vast cosmos teeming with life? Or might it exacerbate existing divisions and conflicts? Would it challenge religious beliefs, or would it be readily incorporated into existing theological frameworks? These are questions that thoughtful people are already beginning to grapple with, in anticipation of what many believe is an inevitable discovery. The timeline for potentially detecting life on exoplanets is uncertain and depends on many factors, including funding for proposed missions, technological developments, and simply luck in terms of whether nearby habitable planets actually host detectable life. But many scientists working in the field believe that we have a reasonable chance of detecting potential biosignatures within the next 20 to 30 years, perhaps even sooner if we are fortunate. This means that children being born today could grow up in a world where the existence of extraterrestrial life is a confirmed scientific fact, rather than speculation. The generation currently in school might be the one that makes this discovery or benefits from it. This lends a special urgency and excitement to current exoplanet research and to the training of the next generation of astronomers and astrobiologists. The Technical challenges remaining before we can confidently detect and confirm biosignatures are significant, but not insurmountable. We need larger telescopes with better instruments. We need more sophisticated models to predict what biosignatures might look like under different planetary conditions. We need ways to distinguish true biosignatures from false positives caused by non-biological chemistry. We need missions that can observe many planets to increase our chances of finding one with clear signs of life, but perhaps most importantly, we need to remain open-minded about what forms life might take and what environments it might inhabit. Our understanding of life is based on a sample size of one, Earth. We know what Earth life looks like, how it functions, what it needs to survive, but we do not know whether life elsewhere would follow the same patterns, or might be radically different in its biochemistry, metabolism, or environmental requirements. This is why the exploration of extreme environments on Earth has become so important to astrobiology. By studying extremophile organisms that thrive in conditions previously thought too harsh for life, such as deep-sea hydrothermal vents, acidic hot springs, the dry valleys of Antarctica, or miles beneath the Earth's surface, we are expanding our understanding of life's potential and the range of environments where we might find it elsewhere. These studies have revealed that life is far more resilient and adaptable than we once believed. Organisms can survive and thrive in conditions of extreme heat or cold, extreme acidity or alkalinity, high pressure, intense radiation, complete darkness, and with minimal nutrients. If life on Earth can adapt to such extremes, then the range of potentially habitable environments on exoplanets might be much broader than we initially thought. This brings us back to some of the exotic exoplanets we have discovered. While a lava world like 55 Concrete East still seems definitively hostile to any conceivable form of life, other exotic environments might not be so clear-cut. Could life exist in the atmosphere of a hot Jupiter, floating in the clouds and never touching the solid surface? Could life emerge in the subsurface oceans that might exist on large rocky planets with thick atmospheres, even if the surface is inhospitable? Could life survive on a tidally locked planet like Proxima Centauri b, adapting to the unique conditions of the Terminator zone? We simply do not know the answers to these questions yet, but the fact that we can now ask them based on observations of real worlds rather than pure speculation represents tremendous progress. The universe has already surprised us many times with the diversity of planetary systems and the range of conditions that exist. It may surprise us again when we begin seriously searching for life and discovering what forms it can take. The synergy between different areas of planetary science is also important to recognize. Studies of exoplanets inform our understanding of Earth and the other planets in our solar system, and vice versa. Understanding how Earth's climate has changed over billions of years helps us model climate on exoplanets. Studying the atmospheres of Venus and Mars helps us understand atmospheric evolution and loss, which is relevant to exoplanet habitability. Exploring potentially habitable moons in our solar system, like Europa, Enceladus, and Titan, gives us insights into alternative habitable environments. In fact, the search for life in our own solar system and the search for life on exoplanets should be viewed as complementary rather than competing efforts. Both are important components of astrobiology. Discovering microbial life in the subsurface ocean of Europa or in ancient lake beds on Mars would be tremendously significant, even though these would not be truly independent origins of life, since material can be exchanged between planets in the solar system. But such discoveries would still teach us about life's adaptability and give us better ideas about biosignatures to search for on exoplanets. Looking ahead to the coming decades, the field of exoplanet research seems poised for continued rapid advancement. The technological trajectory is clear: larger telescopes, better detectors, more sophisticated analysis techniques, and perhaps eventually direct imaging of Earth-like exoplanets at visible wavelengths showing surface features like continents and oceans. Beyond just detecting life, there is the tantalizing possibility of detecting intelligent life through technosignatures or SETI. While the odds of success in any given observation are low given the vast number of possible locati, ons, and the vast spans of time over which civilizations might exist, the implications of a positive detection would be so profound that the search is undoubtedly worth pursuing. The discovery of exoplanets has also sparked innovation in many related fields. new types of detectors, new data analysis algorithms, new approaches to optics and telescope design, all driven by the challenges of exoplanet research, have applications beyond astronomy. The massive datasets produced by surveys like Kepler have driven advances in machine learning and artificial intelligence as researchers develop automated ways to identify planet candidates. Among millions of light curves, the international cooperation fostered by exoplanet research is also noteworthy. Major telescopes and missions involve collaborations among multiple countries and institutions. Data is generally shared openly among researchers. Worldwide, this cooperative approach has accelerated progress and helped avoid duplication of effort. As we move forward with even more ambitious missions, this international cooperation will become even more important. One of the most exciting aspects of exoplanet research is that it remains a relatively young field where major discoveries are still common and where creative new approaches can still make a big impact. Unlike some areas of science that require massive teams and billion-dollar facilities just to make incremental progress, exoplanet research still offers opportunities for clever individuals or small groups to make significant contributions. The field also provides opportunities for public participation through citizen science projects. Programs like Planet Hunters allow volunteers to examine data from surveys like Kepler and help identify potential planet candidates that automated algorithms might have missed. Several confirmed exoplanets were first identified by citizen scientists, demonstrating that you do not need a PhD in astrophysics to contribute to this exciting field. As we reflect on the journey from complete ignorance about exoplanets just a few decades ago to our current detailed knowledge of thousands of diverse worlds, the progress is nothing short of remarkable. The pioneers who risked their careers to search for exoplanets, when it was considered a fool's errand, have been vindicated spectacularly. The taboo subject has become one of the hottest areas in astronomy. The transformation of exoplanet research from fringe speculation to mainstream science has been swift and complete. Today, major observatories routinely dedicate significant time to exoplanet observations. Graduate students can safely build their dissertations around exoplanet topics without fear of damaging their career prospects. Funding agencies recognize exoplanet research, and particularly the search for biosignatures, as high-priority areas worthy of major investment. In conclusion, the story of exoplanet discovery is ultimately a very human story about curiosity, perseverance, technological innovation, and the deep-seated need to understand our place in the cosmos. It is a story about scientists who dared to ask big questions and who refused to accept that some mysteries were beyond our reach. It is a story that demonstrates the power of the scientific method to expand our knowledge and transform our worldview. From the first detection of a debris disk around Beta Pictus to the discovery of the first exoplanet around a sun-like star, to the revelation that potentially habitable worlds are common throughout our galaxy. Each step has brought us closer to answering one of humanity's most profound questions. Are we alone? We do not yet know the answer to that question, but for the first time in human history, we have the technological capability to find out within the lifetimes of people alive today. We may make the discovery that life exists beyond Earth. We may find that our galaxy is teeming with life, that we are just one example among billions of biospheres scattered among the stars. Or we may find that life is exceedingly rare, that despite the abundance of potentially habitable worlds, the emergence of life requires such an improbable sequence of events that it has happened only a handful of times in the entire history of our galaxy. In that case, we would learn that we are extraordinarily precious and unique, that our existence is a cosmic miracle unlikely to be repeated elsewhere. Either answer, whether we find we are one among many or alone in the cosmos, would be profound and transformative. Either answer would fundamentally change how we view ourselves and our responsibilities to preserve the precious phenomenon of life. The universe is vast, ancient, and full of wonders we are only beginning to discover. The era of exoplanet exploration has opened up new frontiers and shown us that the cosmos is far stranger and more diverse than we imagined. As our technology continues to improve and our knowledge continues to expand, who knows what other surprises await us? The journey of discovery is far from over. In many ways, it has only just begun. The first phase of simply finding planets and proving they exist is largely complete. Now we enter the second phase, the search for life itself. This next chapter in the story of exoplanet research promises to be even more exciting than the first. We stand on the threshold of potentially answering questions that humans have asked. Since we first looked up at the stars and wondered what secrets they might hold, the tools we need are being built, the missions are being planned, and the astronomers and astrobiologists who will make these discoveries are already at work. Whatever we discover in the coming decades, whether signs of life or definitive evidence that Earth-like habitable worlds are common or rare, whether techno-signatures from civilizations among the stars or profound cosmic silence, the knowledge will be transformative. We are living through one of the great ages of exploration and discovery, and future generations will look back on this era with wonder. The story of exoplanets is ultimately the story of humanity's quest to understand our context in the universe. It is driven by the same curiosity that led our ancestors to explore Earth, to map the continents and oceans, to venture into space and walk on the moon. It is the same impulse that drives all science, the desire to know the truth about the world around us, however strange or unexpected that truth might turn out to be. As we continue this grand adventure of discovery, we can be certain of one thing: the universe will continue to surprise us, continue to challenge our assumptions, and continue to reveal wonders we never anticipated, and that, perhaps, is the most exciting prospect of all.